Do you know plate girders are used in buildings and bridges when rolled sections do not have enough moment capacity? Plate girders are used to support heavy vertical point loads over long spans. In very simple terms, plate girders consist of two flange plates welded to a web plate forming an I section. The primary function of top and bottom flange plate is to resist bending, and the main purpose of web plate is to resist shear. In this lecture, you will learn about design process for plate girder as per Eurocode 3 part 15. This is part 19 of lecture series on steel design. For other parts, please have a look at link down below in the description. Hey friends, if you're new here, my name is Dr. Qureshi. I'm a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. In this lecture, I will talk about design of steel plate girders as per Eurocode 3 part 15. The learning outcomes of this lecture, by the end of this lecture, you will have all the information that you need to be able to design a steel plate girder. First, I will talk about what is steel plate girder, then real life examples, then initial sizing of plate girders, then the design process as per Eurocode 3 part 15. First, what is steel plate girder? In simple terms, steel plate girder is a built-up beam which has got flange plates, top and bottom, and it has got web. The design is mainly controlled by shear design of webs. These are top and bottom flanges, and in between flanges, you can see these web stiffeners, and in real life, you can see these web stiffeners over here. When it is formed, it is built as I section. Now here are some real life examples. This is London Stratford station where you can see these plate girders. These are the curved plate girders with these stiffeners. Mainly we use these plate girders in stations and platforms. Now plate girders are also used in railway and road bridges, and here are some real life examples. And here you can see that this plate girder has got some varying depth at the location where it has supports, and this is a constant depth plate girder. Plate girders are sometimes used in buildings as well, and these are used as transfer beams. In case of grid mismatches, here you can see that this portion in this building 4 Pancras Square, London, the ground floor portion needs to be column free. That means that there is a grid mismatch for top floors. In that case, we need a heavy beam which can transfer loads from columns from stories above. In this building, the span is as much as 27 meter, and these column loads, they need to be carried on this plate girders. And here you have this heavy plate girder. And again, this shows the construction process for this building. First columns are erected, then after that this heavy plate girder is erected. You can see that wherever the columns are being supported from stories above, you have these web stiffeners. These web stiffeners ensure that there is no shear buckling in plate girders, which I will explain in a minute. If you're thinking that I invented all the design formula, then you are absolutely wrong. I've taken these design formula from Eurocode 3 part 15 and this book, Steel Designer's Manual. So all material has been taken from this book. First, introduction. Plate girders are used to support heavy concentrated point loads over long spans. We use plate girders when the rolled sections, they do not have enough moment resistance. They do not have enough depth. Most of the time, rolled I section, the deepest section available is 1 meter. Sometimes the applied moment is so much that it cannot withstand the heavy loads. Top and bottom flanges resist axial compressive and tensile loads. Mainly, bending is resisted by flanges. Web of plate girder resists shear mainly. The design process is given in PSEN 1993 part 15, which is design of plated structures. Now, pros and cons of plate girders. First, the advantages. Low cost. The fabrication of plate girders is automatic as compared to box girders and trusses, which still use manual fabrication. The material is used optimally, and we have freedom to choose the section as we like. That gives us the design flexibility. Variable depth plate girders are also becoming common. Now, some disadvantages include They are heavy to transport, and no provisions for web openings are there. There are some concerns about stability of compression flanges. Now, this is the 5-stage design process that I'm going to follow. First, initial sizing. The next 4 steps, they are related to the detailed design. So first, we will come up with the dimensions of web and flanges, then bending check. Bending check is mainly related to flanges, combined bending and shear, and finally shear buckling check. Mainly the design process is controlled by shear buckling check. So let us talk about first initial sizing. In initial sizing, first we need to choose the depth of the plate girder. In this lecture, I will be talking about design of plate girders mainly related to buildings. So this does not cover design of plate girders for bridges. These are span to depth ratios. If you have simply supported plate girders, then span to depth ratio is 12 to 20. For continuous girders, it is 15 to 20. And for simply supported crane girders, it is 10 to 15. Then we will choose the flanges. CF over TF means flat portion of the flange divided by thickness of flange. It should be less than or equal to 14 epsilon. The web should be CW over TW. CW is flat portion of web divided by thickness of web should be less than or equal to 124 epsilon. Now, if you recall in section classification of beams, these are limits for class 3 sections. So table 5.2, we have these 4 classes. Class 1 is where moment capacity is reached, and we have high rotation. Class 2 is moment capacity is reached, but we have less rotation than class 1. Class 3, where plastic moment capacity is not reached, we depend on elastic properties, and we have limited rotation capacity as well. Class 4, we use effective properties. If you wanted to have a look at these section classification, I have a YouTube tutorial on a section classification. Now here you can see that this is the limit for class 3. So mainly we will limit the size of the plates to class 3, although slender plates are allowed as well. Beyond class 3, we can absolutely use them. For non-composite plate girders, the flange width has to be 0.3 to 0.5 of the depth of the section. Stiffeners. Now, longitudinal and transverse stiffeners are used in plate girders to be able to stiffen the web. Longitudinal stiffeners are not used in buildings. Only transverse stiffeners are used in buildings where we have to support heavy concentrated point loads or where we have the supports. Intermediate stiffeners, they are usually spaced such that the aspect ratio is between 1 to 2. Sometimes pair of stiffeners are used at the end supports, and this is termed as rigid end post. I will describe this a little bit later. Overhang beyond support is limited to 1/8 of the depth. Area of flange is given by AF is equal to Mx over HW into Fy. Mainly moment resistance is provided by flanges. Moment resistance is equal to force into flanges multiplied by the lever arm between these two flanges. And this formula has been derived from this idea. Now, the next step is to dimension web and flanges, and these 4 steps are related to detailed design of plate girders. Now let's talk about detailed design. Plate girders are subjected to shear forces and bending moments. Detailed design check include in-plane bending resistance, shear resistance, and combined shear and bending resistance. But mainly the design process is controlled by checking the shear of plate girders. Bending is normally fine. Combined bending and shear is also fine in most of the cases. For laterally unrestrained girders, lateral torsional buckling should also be checked. Now, how do we size the web and flanges? Now, minimum web thickness to avoid serviceability issues. For unstiffened web where we don't have any stiffness, TW should be greater than equal to HW over 250. But most of the time we will be using transversely stiffened webs where A is equal to distance between 2 webs. HW is height of web. For the case of A greater than HW, we have this formula, and for other case, we have this formula. Now, we have to specify minimum web thickness for ultimate limit state as well. So to avoid compression flange buckling into web, that is termed as flange-induced web buckling, we use thickness of web as using this formula, where AW is the cross-sectional area of web, AFC is the effective cross-sectional area of compression flanges, HW is the height of web, TW is the thickness of web, and K depends on utilization of the section in bending, which will be discussed in next slide. Now here we have values of K. First value of K is 0.3, where we have plastic rotation is utilized, which means that it is a class 1 section, and second one is plastic moment resistance is utilized. This is a class 2 section, and third one is elastic moment is utilized, which is class 3 section. Now we have covered two design processes: initial sizing and dimensioning web and flanges. After these first two steps, initial sizing and dimensioning web and flanges, the third step is to check bending moment. This step is same to what we did in design of beams. MED over MCRD should be less than or equal to 1. For class 1 and 2 section, MCRD is using this formula. After these first three steps, initial sizing, dimensioning web, bending moment check, we will check combined bending and shear. The formula for combined bending and shear, they are divided into two parts. First is stocky web, means web is not likely to be affected by shear buckling. These formula are same as we did for beams. When applied shear is less than or equal to 50% of the shear resistance, no reduction in bending moment is required. When it is more than 0.5 of shear resistance, then we reduce the bending moment using these formula, and these formula, they come from BSEN 1993 part 11. What happens when we have slender webs? It means that when we have class 4 webs, in this case, webs are subjected to shear buckling, and we will use these relation, and these comes from BSEN 1993 part 15, which is for plated structures. So bending and shear, if VED is less than equal to 0.5 of BWRD, then no reduction in design moment is required. If VED is greater than 0.5 BWRD, you can see that here we are only considering design shear resistance of web. We are ignoring flanges here. So when we have shear buckling, then shear is mainly provided by web. When BED is greater than 0.5 BBWRD, we use this formula, MED over MPLRD plus 1 minus MFRD divided by MPLRD into bracket 2 VED over VBW minus 1 whole square. This should be less than or equal to 1. Now, once we have performed these four checks, initial sizing, dimensioning web and flanges, bending check, combined bending and shear, the final check is shear buckling check, and the design of plate girders will be mainly governed by this check. Design of plate girders is mainly governed by shear design of webs. There are two classes. One is stocky webs, when web is not likely to buckle and shear. For stocky webs, failure is by yielding, and we use normal VPLD formula, which is equal to AVFY divided by under root 3 over gamma m naught, and HW over TW should be less than or equal to 72 epsilon over nu for unstiffened webs. And for stiffened webs, we use this formula where K tau is a shear buckling factor. We use these two formula to work out shear buckling factor, and they depend on A over HW ratios, which is the panel ratio of transverse web stiffeners. How about if webs are not stocky, they are slender webs? It means that they are class 4 webs. Anything which is beyond these two limits of HW over TW, the failure will be by shear buckling, and it will consist of two components. One is shear web and other is shear provided by flanges. And this formula should be less than or equal to nu FYW HWTW over under root 3 gamma M1. Shear buckling factor K tau can be found out using this graph as well, which is the graph between shear buckling factor and web panel aspect ratio A over HW. And from here, first we work out web panel aspect ratio, and then we draw a vertical line, and then from here we can directly work out value of K. Now, how does web fail? So in picture A, you can see that web is under pure shear. In next figure, tension field develops due to shear, and this is the post-buckling stage. And finally, mechanism happens and web panel shears in this way. And in real life, you can see this picture over here. Shear resistance web design. For slender webs, when web is susceptible to shear buckling, the shear resistance is defined by two components. One is by web contribution, other is by flange contribution. And these two are given in BSEN 1993 1-5. First, let's talk about the contribution by web, which is given by this formula, where KW is a reduction factor, and our entire aim here will be to find out this reduction factor. And this reduction factor depends on end post, whether they are rigid or non-rigid, which I will define in a minute in the next slides. First, we have to find out web slenderness ratio, which is equal to tau YW over tau CR under root. And this is equal to 0.76 under root FYW over tau CR, where tau CR is equal to K tau sigma E, and sigma E can be found out by using this formula here. We put value of E and value of epsilon and value of nu, which I think would be about 0.3 something, and we get roughly this value. If we put all these values back into this equation, we will be able to get tau CR, and once we have tau CR, if we put it back in here, we will get value of lambda dash W, which is web slenderness ratio. Again, putting all these values, we get value of tau W as HW over 37.4 TW epsilon under root K tau. Now, this is the slenderness ratio. It will tell us that if web is slender or not, and also it will give us an idea about how we can find out the reduction factor. Now, reduction factor will depend on this tau W value. If it is less than 0.83, then for rigid end post it is 1, non-rigid it is 1. If it is in between 0.83 and 1.08, then we have these two formula, and if it is more than 1.08, then we use these bottom two formula. Now, what does it mean by rigid end post and non-rigid end post? Let us see. You can find out value of reduction factor using this graph as well for rigid and non-rigid end posts, which is a quicker way to find out the reduction factor. What does it mean by rigid end post? Rigid end post consists of two double-sided transverse stiffeners as shown here, or it consists of rolled section. Here there's a rolled section as well. So when a pair of web stiffeners is used, it is termed as rigid end post. On the other hand, a non-rigid end post consists of only a single double-sided stiffener, which is here, and they do not need to be designed to carry tensile anchorage force since they are assumed to be resisted by web itself. Up to now, we have found out the contribution of web to shear resistance. Now we will find out contribution of flange, and contribution of flange to shear resistance can be found out by using this formula, where value of C is calculated using this formula. Again, these design provisions, they come from clause 5.41 of Eurocode 3 part 1.5, which is for plated structures. Web stiffeners. Web stiffeners are required for slender webs so that shear buckling does not happen. And there are two types of web stiffeners. One is intermediate web stiffener. The purpose of this stiffener is to increase the capacity of web. Other is bearing or load-bearing stiffeners. They prevent local failure of web under concentrated point loads or reactions to the flange. In real life, these two stiffeners can be seen. So transverse web stiffeners are away from the supports. Here we have bearing web stiffener, and in addition we have these jacking stiffeners as well. The purpose of these jacking stiffeners is for maintenance. So when we have to lift this bridge girder for maintenance, there should be some point where it could be lifted so that the bearing over here can be changed. And jacking stiffeners are designed similar to load bearing stiffeners. Now, how do we design web stiffeners? For web stiffeners, H over TS should be less than or equal to 13 epsilon, which is very close to class 3 limit, which is 14 epsilon, where HS is the outstand width and TW is the thickness of stiffener. Now, these requirements again are from 9.28 clause of BSEN 1993 1.5. Intermediate web stiffeners. The second moment of area of intermediate stiffeners depends on web panel ratio A over HW, can be found out by using this formula. The effective dimensions can be found using these relations. This is a single-sided and double-sided web stiffeners. Effective cross-section should be able to resist a compressive axial force arising from shear-induced tension field plus
any externally applied loads and moments. So let's work out PEDs. For PED, again, depends on A over HW ratio. Tau CR is the shear stress, and sigma X ED and sigma CR will be defined in next slide. Sigma CRX is elastic plate buckling stress for web under direct longitudinal compression, and tau CRX is elastic shear buckling stress of the web, and tau XED is the longitudinal direct stress in web. It should be taken as 0 for symmetric sections, and it should be taken as algebraic sum of stresses at top and bottom of the web in asymmetric sections. How do we design web stiffeners? In simple terms, web stiffeners are designed as conventional compression members or column members in accordance with Eurocode 3 Part 11, but using curve C for buckling curve. What is elastic critical buckling length for these stiffeners? As stiffeners are fixed between flanges, so LCR is taken as 0.75 HW. How about when we have combined axial load and bending? So for combined axial load and bending, we use this expression from clause 6.3.3 of Eurocode 3 to work out the capacity. Again, note that there is no amplifier applied to MZED since the web prevents the buckling in the plane. And again, these are different sign conventions for single-sided and double-sided web stiffeners. Bearing or load-bearing stiffeners. A bearing stiffener should be placed symmetrically about the web centerline. The design checks are same as intermediate stiffeners. For bearing stiffeners that also act as rigid posts, additional bending moment from anchoring of tension field must be considered in addition to support reaction. Thanks for watching. This is the end of the lecture. In my next lecture, I will be solving a practical example of plate girder. So please keep watching.